How are you doing, Pradeep?
Yeah, I'm good.
So we'll
How
give
are you?
it 5 more minutes to see who else comes. I think Miklos wanted to come. Ruth is not gonna be able
Okay,
to make it today.
okay.
So we'll see if Miklos makes it.
Yeah, yeah.
Did you have a good day today?
Yeah, so far good.
That's good.
Yeah. So the code, like, we won't be able to compile it in local, or is it possible to compile?
Yeah, you can compile it locally, but it doesn't always work the way that it's supposed to. So
Okay.
Flow has something called the local net. So
Mm.
I'll
What
send
is
you,
that local net?
huh?
What it is? Local net?
Yeah, so I'll put the code in the chat right here. I mean the
Okay.
GitHub link in the chat. So
Okay.
what LocalNet does is it create a simulation of a certain amount of flow nodes interacting with
Mm-hmm.
each other on your local environment. So you run
Okay.
that, and it uses it uses the GitHub repo. You initialize
Mm.
it, and it should work. So there's some problems. It has a bunch of dependencies. It wasn't working on Mac processors, but I don't think you use a Mac anyways. So it should try it, run it. You're obviously gonna need to have you're gonna need to have the Flow Go repo on your device, but it should work.
Okay.
Let me know if you have any issues. We tend to have a lot of
Okay.
issues just
Okay.
getting it to compile and run.
Hi
Miklos,
there.
hey Miklos,
I saw your car.
you're still in the car. That's fine.
Yes, my phone has some recharging issues, so I might lose connection. Let's just try.
No problem. Just sit in for whatever you can. I think it'll be interesting. It's recorded anyways if you want to catch up on it.
Sure. Thanks.
Sure, no problem. So let's go ahead and get started. Okay. So we did an introduction to blockchain. We'll do an introduction to Ethereum now. Ethereum more closely resembles Flow. So this will be more of a technical presentation than our previous one. As always, stop me if you have any questions. So we're going to be going over four major things: the history and overview, the fundamental architecture, utilities and use cases, smart contracts, and dApps. So we're going to talk about what is Ethereum, introduction to Ethereum, what makes Ethereum different than Bitcoin, and then we'll talk about the way that blocks and nodes and consensus and security is done on Ethereum, and we'll introduce another concept called forking. We'll also talk about various utilities and use cases, software development environments for Ethereum, IDEs, CLIs, test nets, and test nodes. And then we'll get into smart contracts and dApps. Okay, introduction overview. So what exactly is Ethereum? Ethereum is an open source blockchain network which incorporates computation. So like we discussed last time, Bitcoin was just a database where you updated the ledger with entries and they were representative of transactions. Ethereum changes quite a few things about that formula. It adds computation, and it adds, when you add computation in addition to storage, then you open the door for a lot of things. So we'll see. So it was the second major blockchain. There was Bitcoin, and then the second major one was Ethereum, and that was in 2015, about 7 years after Bitcoin was initially released. So it's more of a general purpose blockchain. Bitcoin is primarily for transactions. That's pretty much the only thing you can do with Bitcoin. Ethereum is more general purpose and adds other functionalities and features to this idea of decentralized ledgers. So in addition to being a decentralized ledger, it also has decentralized computation. So it has the regular old decentralized databases, which is the whole innovation of blockchain, initial innovation, sorry. But it also adds storage, which we have talked about a little bit, and networking and computation, which I talk about. And then it has a peer-to-peer currency, which is Ether, which is similar, it works very similar to the way Bitcoin works. So instead of Bitcoin, there's Ether, and it's the native digital currency. So just like Bitcoin, Ether has no intrinsic value outside of it just being a database update and ledger entry on the blockchain. Right now, Ether has a market cap of 29.5 billion. And the average time it takes to mine a block on Ethereum is about 13 seconds, which I believe is faster than Bitcoin. I think Bitcoin takes about a minute or two. So then there's dApps and smart contracts, decentralized applications of smart contracts, and it's code which monitors the transfer value. So we'll talk about that. They can have programmable conditions, and not only is it contracts, but you can have various kinds of decentralized applications and even more decentralized complex systems using Ethereum. There's a concept called decentralized organizations, which we'll get into later. Questions?
No.
So I know Miklos is just listening in, so we'll just keep going. So these are some of the fundamental basics of the Ethereum. It's a different blockchain. One of the main innovations it adds are smart contracts, but also adds something called oracles, which we'll talk about. It has a decentralized virtual machine, which, as you can see, Flow also has a Flow virtual machine. So we'll talk about that. It executes scripts using public nodes. It was created by Vitalik Buterin in late 2013, and it was funded, initial development was funded by the sale of Ether in 2014. It's written in Solidity, which basically just means it's written in C++ and JavaScript, but then they called it Solidity and built a little client library on top of them. So some of the main challenges that it sought to attack with Bitcoin's blockchain was scalability. So instead of proof of work, they created something called proof of stake for a consensus, and we'll get into that a little bit more. We've discussed it already, but we'll go over it in a little bit more depth. The initial version of Ethereum was called Homestead, and they have a final like end goal version that they want to get to, which is called Serenity. There's decentralized applications called dApps. Most ICOs, initial coin offerings, are run on Ethereum, and Dapper broke Ethereum. That's why they created Flow. Questions?
So this proof of stake, I know, but what is the proof of work?
So you want to talk about
We
proof of
discussed.
stake?
We discussed proof of stake last time. So it is like so when we when someone validate the transaction, they will stake all their Ethereum will be staked.
Yep.
And yeah, so what is mean by proof of work?
So proof of work is when you have nodes, full nodes called miners, and there's a nonce that's at the top of a block header. So for you to commit a block to the blockchain, you have to guess that nonce. And it can only be done by brute force, just trying to guess whatever that nonce is, which is like a double hash of the previous block header. And then when you guess it based on your computational effort, then the block gets added and you also get rewarded. So that's proof of work. Proof of stake is what you described.
So to compute that nonce is what it takes more processing and time.
Yeah, proof of work, it takes a lot more processing power. Yep, it's computationally difficult. Other questions?
That's all.
So what makes Ethereum different than Bitcoin? So we see here we have a direct comparison between Ethereum and Bitcoin. The founder is unknown, Satoshi Nakamoto. Ethereum is Vito Buterin, and the Ethereum team. The smallest unit is a Bitcoin. The smallest unit is called a Wei. The maximum supply of Bitcoins is 21 million. There's no maximum supply of Ethereum. The block reward for committing a block is 12.5 Bitcoins. And it will be halved. I think it's halved already. Actually, it's like 6.25. For Ethereum, you get 2 Ether. You collect transaction fees in Bitcoin. On Ethereum, you collect something called gas, which is just kind of transaction fee. The consensus algorithm is proof of work. Here, it's proof of stake. It's proof of stake now. The purpose is a decentralized payment system. The purpose is to be a decentralized supercomputer. Not only it is also a payment system, but it also acts as a decentralized computation force. Questions?
No.
So now we'll look at the fundamental architecture behind it. So this is storage. This is the same stuff we already covered before, so we won't go over it again. Do we have any questions about storage, on-chain storage, off-chain storage? This is your chance to ask any questions. Maybe you went through something in the document or you're just curious about it. If you don't have any
I'm good.
questions, we can just move on. Okay, great. Forking. So what is forking? Forking is when you have a pre-existing blockchain, but you want to change something about the protocol. So when you want to change something about the blockchain protocol, how it proceeds, whether it's pertaining to consensus, whether it's pertaining to nodes or networking or storage or computation, you can't just shoot out a software update to a blockchain. So blockchain is obviously decentralized. So there's all these nodes and it has to be the same thing for them to reach consensus. So what happens is you'll have 2 nodes on the network that can't agree about something. Maybe they want to change the way that the blockchain operates, or there's a transaction which is disagreed about. So when there's nodes that can't agree, then what happens is part of the nodes, they add the change to the way that they deal with that blockchain. And part of the nodes stick with the old way that the blockchain used to be. And what that does is it basically makes a new blockchain, which is the one that was changed. And this causes it to split into 2 or 3 chains. So that's forking. Forking happens due to adding new features or security or invalid transactions. So there's 2 major kinds of forks: soft forks and hard forks. A soft fork is where you can change something and the old blocks are still compatible with the new blocks. So it's backwards compatible, basically. So an example of a soft fork was a SegWit update to Bitcoin, and it added a new kind of addresses, Beach 32, but it didn't invalidate the old P2SH Bitcoin addresses. So this was a soft fork where it made a minor change and the old stuff was still compatible. But then there's a hard fork. A hard fork is when you change something fundamental about the software running on full nodes or network peer behavior. So the new blocks are going to get mined under some different rules. When that happens, either everybody needs to change to these new rules, or some people will change to new rules and some people won't. And so there will be 2 versions of the same blockchain. So this can sometimes create a new currency because the old blockchain is using what is recognized on that, and the new forked one is using what's recognized there. So that's in Ethereum, that's called Ethereum and Ethereum Classic. On Bitcoin, that's called Bitcoin and Bitcoin Cash. And then they're interchangeable with each other. So the biggest fork in Ethereum is called Casper. Casper changed Ethereum from proof of work to proof of stake. And if you don't upgrade to Casper, to the proof of stake version of Ethereum, you can't get played consensus. And the full nodes that don't install Casper are incompatible with the ones that do. So this already happened a couple years ago. Probably everybody is running the new proof of stake version of Ethereum. Does the idea of forking make sense?
Yeah.
So obviously, if you want to stay within a particular blockchain, then you just fork that one. This only applies to FOSS blockchains, open source blockchains. If your blockchain is owned by a company, you can make as many changes that you want, and everybody will be forced to accept those changes. So there's no forking on Flow
Okay.
because the public doesn't control Flow. Flow is within the hands of Dapper. So they make the changes, they change the protocol as much as they want, and all the nodes will be forced to accept it. In the future, when Dapper is not directly controlling the code base in that way, then there could be forking. But right now, there would be no forking. So you can think of forking almost like having your own repo that people are pulling up. You copy the repo, you make changes, and people use that instead of the other one.
Got it.
Any questions about forking?
No.
So Ethereum is not a fork of Bitcoin. Ethereum is its own thing.
It's okay.
So consensus of verification, we talked about consensus. Proof of stake, we talked about consensus. This is how they agree with each other. And we talked about proof of stake, which is relevant now. So are there any other questions about the basics of consensus?
No. So consensus are to validate the transactions, right?
Yeah, to validate the transaction. So everybody agrees on it. Yep. So proof of stake, we've talked about it before. This is what Ethereum uses. They actually invented proof of stake. The stake is divided between stakeholders. It's based on your status on the market. The owner of the block is determined deterministically. There's no block rewards. The currency are issued at the beginning. And then people get gas fees. And then a certain amount of the currency is created when a block is committed. Questions?
No.
So we talked about Merkle trees. I don't think we need to go over Merkle trees again.
Mhm.
So we know how transactions work. We understand the idea of wallets and how they communicate, and private keys and public keys and all that stuff. Great. Okay. So now Ether. Ether is the native currency that lives on Ethereum. It's a currency for transactions, and it provides the fuel, the gas for applications on Ethereum. Every block which is validated generates 2 Ether and gives us a successful node. But there's no limit to Ether, unlike Bitcoin, and the smallest denomination of Ether is called a weight. So very simple. Questions about Ether?
Maybe a generic one. So you told like so for example, like Bitcoin, we have limited number of Bitcoins, but only the half of them is mine, right? The remaining is still not mine. So what? So mining like is just like validating the transaction, or anything else also considered as mining?
Mining is when there's a block that already has collected transactions, you validate it using your processing power, and you guess the nonce, and that's it.
Okay, that is the mining. So whoever like validates the transaction, they will get the new coin. Means like the new one from the pool. Okay.
Yep.
Okay.
So we know what nodes and network peers are. We've discussed that, and we know how networking works in blockchain technologies. So let's look at a client. So we'll start noticing some similarities to what we're working on now. So a client, you can think of this almost like an observer service. A client is software that connects to the blockchain, and it verifies your local copy of blocks. But it also turns your computer into a lightweight node, and it contains interfaces for adding transactions. But the problem is when more dApps are deployed, decentralized apps, which we'll talk more in depth about later, congestion increases on the network, and that decreases transaction speed and also increases gas fees. So that caused the congestion of all these people running clients and updating the network. It brought Ethereum to a halt. So you have these clients, and they directly can interface as a lightweight node with the Ethereum network. They can send transactions, and they can interact with dApps. So when there's too many of them, it causes congestion on the network. So this is why in Flow, we have something called the observer service. The whole purpose of the observer service is so that these clients, which are easy to run, never directly interact with the network. They never congest the network. They're never able to make changes which are not pre-screened. They act as a proxy to avoid that exact problem. So two popular clients for Ethereum are Aleph and Geth, which stands for Go Ethereum. And usually Ethereum clients are either written in Go, C++, or Python, and they're available for all operating systems, Windows, Linux, Mac. The clients also can run something called the EVM, which is the Ethereum virtual machine, which we'll talk more about later. And they help users perform transactions on the network and interact with smart contracts. And most clients are open source, maintained by their communities on GitHub. Questions?
So the flow is like forked from Ethereum. Means
Yeah,
like it's
Flow
great.
is not directly, but they originally, the company was a Ethereum video game company. They were making video games as dApps on Ethereum, but their video game became really popular and it exposed some of the problems with Ethereum. So they said, you know what, let's make our own blockchain that solves these issues.
But it is like it's completely like a different one, but it is based on the Ethereum, right?
Yeah, it's completely different. It's not a fork. It's
Okay.
independent blockchain.
Okay.
But it does have some ability to interact with the Ethereum blockchain. So we'll talk about that later, but it's separate.
Okay.
So let's look at the two most popular Ethereum clients. This is the logo for Geth. So clients, like we said, are similar to an observer service. So Geth is Go Ethereum. It's written in Golang. And I see Jim. Hey, Jim.
Hey. Don't let me interrupt. Keep going.
So we said the clients are similar to the idea of an observer service, with the difference that they directly update, which is problematic. So let's look at the two most popular Ethereum clients. We have Geth and Parity. So Geth is written in Go, and it's actually a CLI client. And what it does is it runs a lightweight node on your system, and it's the most popular one. It's on all the operating systems. It performs transactions, it can send transactions and receive, and it can communicate with smart contracts. So this is not a wallet where you just house your stuff. It actually is a lightweight node that you're using to do various things. So it's open source and the community builds it and maintains it. So you still have to have your wallet to house your tokens and your crypto, but you use this to directly interface with the network. So it's very similar to what an observer service is supposed to. It's very similar to what an access node is now. So you can almost think of this as pretty much the access node, but now we're going to have the staked version and then the observer service, which is the lighter weight client. Then there's Parity, which is the fastest and the lightest client for Ethereum. It's written in Rust. It's also open source, but it has a better reputation for consistency, versatility. Questions? So this is the logo, Jim, for Geth. So it's a little strange character. So we have our wallets. You're muted, Jim. I don't know if you're talking to us.
What was that? Show me the logo again.
Yeah, that's the logo for Geth, which is just.
Oh, I was wondering what that was.
It looks like a minion, I guess, with the evil hat.
Yeah, looks like Darth Vader robot.
Exactly. So kind of weird. Those nerds love stuff like that. So we talked about the wallets where you're shooting the transactions back and forth and holding your tokens. Then we talked about the clients. But what if I want to run a full network locally and try stuff out? Then to do that, you would want to have a local test network. And you use RPC interfaces for your local test nets. So RPCs, remote procedure calls, are distributed commuting procedures. It's where one program causes a subroutine to execute on another computer on the network, and they're written like local procedure calls. The details for that remote interaction are not usually explicitly coded, and it requires location transparency. So when Miklos comes back, I'm just going to do a quick back review just so that he can kind of see what he missed. Hey, Miklos. Just give them a second. So that's how remote procedure calls work. But we know everything on the blockchain doesn't change. So any upgrades to a smart contract have to come from a new address. So this becomes problematic. And it has to be distributed as a new instance at a different address. So I publish a smart contract. I want to make a change to it. I can't just send an update to the blockchain because the blockchain is immutable. So now my smart contract, whatever state that it's in, it could be broken, is just there on the network. So now I have to put another smart contract out. So we can see that this becomes a problem. So because you can't really make sure the smart contract is going to work before, you need test networks and test nodes for development to test your smart contracts, to test your dApps locally in order to make sure that they work. Miklos, I'm just going to quickly go back a couple slides because you missed a couple things. So we talked about clients, and a client is basically the Ethereum equivalent of an access node, lets you update and receive blocks and know what's happening, but there's a congestion issue. So that's why on Flow we have an observer service and a state access node. The most popular ones are Geth and Parity. Then you can go look at the PowerPoint and watch the recording to get all the details on that. Okay. So they had to come up with something, some way for you to create a simulation of the whole Ethereum network, not of just one node, so that you can deploy your smart contracts to a local test network, make sure that it's functional before you actually put it out on the system. But also, let's say you want to change consensus, or you want to play around with the nodes, or maybe you want to change something fundamental, then you need a local test network to do that. So that would be equivalent to, for Flow, we have the test net, the local test net that we run, and we changing things. And that's that GitHub link I sent you pretty earlier. So any questions about that? I think Pradeep froze up. Miklos is still getting out of his car. So Jim, do you have any highly technical questions about remote procedure calls? And local
Well, first of all, yeah, highly technical? No. Remember, I apply the Feynman principle here. Keep it simple.
Keep it simple is really important. I think Pradeep's internet is cutting out, and the Miklos is just getting home. That's okay. I'll just give Pradeep a couple minutes, a minute or two. Ruth is gonna watch a recording, she said.
Okay.
And Sean, I guess he's busy or something. So I'll just wait for Pradeep for a second and just go back
Okay.
over some of the stuff that we went through. So
Go back to the Merkle, by the way.
sure.
Explain this to me one more time. Real
Sure.
quick.
So there's a Merkle root, right? So what the Merkle root is it looks at all the transactions that are put on a block, and it makes a hash of them. So it puts it through an encryption algorithm, and it takes all these transactions and it just makes a short phrase out of them by encrypting them. Almost like the same way that you would create a password or an encrypted password out of a block of text. And that becomes a fingerprint. That can't be changed. The moment that you try to recreate that, but
The Merkle cannot be changed, or the hash?
Merkle root.
Okay.
The hash. Yeah, the Merkle root is the hash.
Okay.
It can't be changed because the moment, like, let's say I was trying to imitate the Merkle, a Merkle root or Merkle hash, and I'm trying to recreate the same exact transactions that are on a block so I can get the same output. It's going to be borderline impossible because there's too many possible variations. So it's a highly accurate representation of all the data that was there. The moment that you change a single thing about any transaction that happened on a block, the Merkle root will represent that. So if you have this,
So the Merkle root will automatically change because it's
exactly.
Okay.
So that makes it so that nobody can really change a transaction, because the moment anybody tries to change a transaction and give you that block,
And this is why, as long as you have the key to translate and uncrypt the Merkle,
you know all the transactions were
you know all the
historical.
transactions. Okay.
But the problem is, okay, am I really going to check the Merkle hash for every single block that has ever existed in history? That becomes a problem. So how do we get around that? The way you get around that is just take two hashes together, hash them, and get one. And now if anything changed about any of the transactions in either one, then it would alter it. So that's why they call it a tree. So I'll just draw a quick diagram.
Interesting. Okay.
So
I'm
here-
now familiar, since you put it in these terms, I'm now familiar with it. I just never heard the term Merkle before.
Yeah. It sounds crazy, but then when it's explained, it's not that bad. So you got this block and it's got all these transactions. So you make this little hash right here,
Mhm.
which is the yellow one. And then you go, you get another block, you put that right here. Now it has its hash right here.
Mhm.
Now, what I'm going to do when I make my next block, instead of including both of the hashes, I'm just going to hash both of those together.
You hash the hashes.
I hash them together. Boop. And now I get a new hash, which was composed of those two hashes, which is this one. And now I only need to check one, and it virtually contains all of the transactions that ever were in this one tiny little piece of text.
Interesting.
So it saves space, it saves time. It's just it's brilliant. It's awesome.
Okay. Got it. Pradeep is back. Thank you for
Yeah.
enlightening me.
Sure, no problem, of course. Now you can confidently talk at dinner parties about working at Merkle hashes and Flow. They have their own like innovation pertaining to that. I haven't even got into it. It's like diagonal acrylic Merkle hashes. I haven't got into. They got a lot of crazy. I know they have some PhDs working behind the scenes that we haven't
Yeah.
met yet.
Ah, okay. So this is where we need to tap into your network now, huh?
Yeah, that stuff is a little bit higher up in my pay. I'm not quite academic yet. Maybe one day I'll be at that level to understand that stuff deeply. So that's the purpose of a local net. Does that make sense, Pradeep?
Yes, yes.
So with a local net, you can change anything about it and then try and run it and see what the behavior is and then test stuff. So this is what we basically work on Flow. When we clone the repos, then what we do is we create a local net, and then that's how we test to see if our changes will work. And then when they work locally, then we push it to the public repo. Okay. So now we're going to look at emulators, Ethereum emulators. So a local network and an emulator is basically the same thing. So there's Ganache, also known as test RPC, which is the most popular, and it gives you a private network or a local net, and it gives you rapid Ethereum or Corda dApp development because you can create your dApp and then deploy it to this local net and see if it works. Deploy, develop, and test dApps in a safe and deterministic environment. And it's normally done in a CLI, but there's also a user interface for Ganache. And you use it as a platform. You run contracts, you build ads, you do tests. It can display profiles of different users, private keys, purchases, balance statuses, logs, debugging, customize your mining settings, block times or production needs, and you can also examine blocks and transfers. Add nodes, remove nodes, so on and so forth. Then there's Pytherium, which is deprecated, is older. It's also for local test networks and to create local nodes. It's lighter than Ganache, but it doesn't have as many features. You can create a Genesis block and start the blockchain. You can create a test state, and you can simulate transactions, but that's about all you can do. Questions about the emulators?
No.
Okay. So emulator is just the same thing as a test net, local net, a local net, not a test net. A test net is something slightly different that we'll talk about. So this is a UI for Ganache. You can see it's a one-click blockchain, the GitHub repo, the docs, and you can just create it locally and mess around with stuff. So there's no UI for the Flow local net quite yet. That's probably a long ways out. Maybe we would develop it, who knows. Then there's test nets. So a local net is for you to play around in a safe production environment on your own machine. Then there's a test net. A test net is basically a fake blockchain. It's a blockchain that runs nodes, but without real money on it and without requiring the same kind of commitment as a real blockchain. So it's used by protocol developers or smart contract developers to test. And it's a production-like environment. It's very similar to Ethereum. They're basically replicas of Ethereum where there's no consequences. And they have the same environmental parameters as the mainnet. So you can test ideas and solutions before you commit them. You can correct mistakes safely. If you break something about it, it's fine. But you can also observe Ethereum behavior live while you're working on it and improve on it, modify it. And all the tokens are worthless on a test net. So there's 4 main test nets for Ethereum: Ropsten, Kovan, Rinkeby, and Goerli. So we'll talk briefly about each one. Does the idea of a test net make sense?
Yeah.
So I believe there is a flow testnet. It's not really useful for us because we're not like testing smart contracts or anything. We're working directly on the protocol. So that's why we use the local net. But I believe there is a flow testnet for the same purposes. So the Ropsten testnet is a proof of work. So it's just like Ethereum, but for consensus, it uses proof of work. It doesn't use proof of stake. And you have to mine to gain the test Ethereum. It's easier though. It's supported by both Geth and Parity, the clients that we were talking about. And it's very similar to mainnet. So there is mining, and the mining works just like it used to when Ethereum was proof of work. So it works the same way. Obviously now Ethereum is proof of stake. The consensus outcomes also resemble the mainnet, and it has very accurate transaction validation simulation. The ether that you mine on Ropsten, you don't have to directly mine it if you don't want to, even though it's easier. There's something called faucets. So faucets are basically like these free online places that you can just put in an Ethereum test address, and it will just give you a whole bunch of fake Ethereum so that you can use it for your testing purposes. Faucets give away simulated ether without the need for proof of work for testing for developers. So it's a proof of work version of the Ethereum blockchain for testing purposes. So this just shows you, this isn't Ropsten itself. Obviously, you would run Ropsten probably in a CLI, but this is just showing you blocks that are mined and committed on Ropsten, transactions, so on and so forth. So then you can search it. You can see, did my smart contract execute? Is it available? Did it work? Did my changes work? So on and so forth. Okay. So then there's Kovan. Most of these are named after like subway stations for some reason in different parts of the world. This is what they did. It's a proof of authority testnet, so it's different. It's not proof of work. It's not proof of stake. So proof of authority is basically you prove who you are on the network. Basically, proof of authority is I own this blockchain or I own this testnet, so I can do whatever I want on it. Basically, admin credentials. So it's centralized. It goes against the very idea of a blockchain, but it's for the purpose of testing. And you request your pseudo Ethereum from faucets. Only selected nodes allowed to create new blocks and validate transactions. And obviously the mainnet doesn't use proof of authority. So this means because it uses different consensus stuff, is very imprecise, but you can still test dApps and smart contracts on it. And it's also resistant to security because Ropsten was attacked a couple years back. So because this one uses authority and you can only be a particular person on the network to add stuff, it gives you more reliable and stable testing environment. So then there's Rinkeby. Rinkeby is also proof of authority, and it's launched by the Geth project. Remember we talked about the Geth client. You still order your play Ethereum from faucets. It's also resistant to spam attacks because it's proof of authority. Ethereum are mined and circulated only when you request it, and blocks are created every 15 seconds. Then there's Goerli. So Goerli
These are
also
all
uses Geth.
components, Ollie. These are all components of Ethereum.
So these are all like fake copies of the Ethereum blockchain that are run by the open source community so that you can test stuff.
Oh,
So this lets you test changes that you want to make to the network, but also lets you test smart contracts and dApps. Because so when you put the smart contract out, because you can't change anything on a blockchain, it basically has to be in a final state. So if it's not in a final state, you know, you're hit. It's going to be messed up. So obviously, if you're dealing with like huge clients or financial transactions, or even if you just want your software to work, you can't just put it on there. So they have all these various test networks. Flow actually, right now, Dapper runs the only Flow test net. Maybe in the future they'll have other ones, but they have a test net as well. So understanding kind of, what the test net is and what it does is important for us as well. We haven't really gotten into like smart contract or dApps or cadence development yet. But if we do, then we would have to be familiar with the Flow testnet for sure, and how it works and how it integrates also with the main Flow repo, considering the fact that they're changing it so much. So I imagine the testnet is really buggy right now,
Got it.
but we haven't played with it yet. So Go Early is also proof of authority and also uses Geth, but the whole purpose of Go Early, so this is interesting. The purpose of Go Early is that it wants you to be able to use any Ethereum client and interface with it. Whatever language or whatever client that you're using, you should be able to use and interact with its testnet. So this kind of goes into one of Dapper's main philosophies and what they want to do with the Flow wallet. So they want the Flow wallet to be able to interact with any blockchain directly and keep your tokens in a centralized place without dependency on any particular client or outlet. You can just keep it directly in your wallet. And they also want to move to doing that in web browsers. So we'll talk about Ethereum web browsers too. So this is kind of setting the stage for the Web 3.0 mentality that Flow has. And so we'll start seeing more of that with this. So we're going to move on from testnets now. Any question about testnets, Ethereum testnets? So now we're going to get to one of the other major. So obviously Bitcoin, it didn't have local nets. It didn't have test nets. There was just a Bitcoin blockchain because all you were doing was updating the ledger. But once you added computation and execution, you needed all of that. You needed development environments for people to test stuff in and make sure stuff works. So now we're going to talk about a really interesting thing, which ties into what we're doing a little bit, which is oracles. So you haven't gotten here too much yet, Pradeep, in terms of what we're doing, but this I think will make more sense to you, Jim, when I start talking about this, and then when I tie it into our current project. So oracles, what is the purpose of the oracle? So blockchains are self-contained. Nothing on the outside can really do anything except update the ledger on a blockchain. But let's say you need particular data for something that you have on the blockchain. Let's say I write a smart contract that executes only when a stock is at a particular price. So I write a put contract. And when Apple stock hits XYZ price, this contract is supposed to sell. But how is my smart contract going to know what the price of Apple stock is if that's not stored on the chain? And furthermore, if I write it to get data off chain, how can I make sure that that data is consistent and that everybody trusts that data? So this is a problem because blockchains are their own networks. They're not connected to the internet. So they came up with these things called oracles. What are oracles? Oracles are basically little pieces of software that act as data feeds, and they connect Ethereum to off-chain data for smart contract usage. That's what they do. So Oracle acts as a middleman for off-chain data so that smart contracts can refer to the Oracle, and that there's a standardized version of important data for smart contracts. Ethereum cannot directly access off-chain data. So because Ethereum can't directly interface with off-chain data, what they did is they create these oracles, which are actually Ethereum compatible smart contracts or dApps in and of themselves to pull data and store them. When you rely on a single point of data, then it becomes insecure and it's not decentralized and it defeats the whole purpose of the blockchain. So you don't want to rely on one single source of data, but you also don't want to rely on an API. If I just have an API on my smart contract, then every single user on smart contract can get different results. So if I deploy a smart contract with API and it pulls data about Apple stock at 10 a.m., that could be $140. But then somebody else pulls that same data an hour later and it could be $130. There could be a lot of volatility in the market. Additionally, APIs can be hacked or they can get out of date, deprecated. And so that would violate consensus if people don't agree on the data and smart contracts execute and other ones don't execute. So that's where oracles come in. Oracles try to make the data objective by having agreed upon data on the blockchain. And any nodes that replay transactions or that sends transactions are going to use the same data. They're not going to use the API to access the most recent data, or they're not going to get the data at different times. They're going to get it from an oracle. So what an oracle actually is they're constructed of smart contracts, which is software. And then they interface with off-chain components, which can then query APIs. The off-chain component updates that oracle at a particular interval, and then whatever that data is, it gets put on the blockchain for everybody to see, and then the smart contract uses it after it becomes immutable. So for example, a market prediction DApp uses oracles to settle payments. So the market prediction DApp is going to interface with the oracle. An oracle is going to get off-chain data about prices at a particular time and post it. Now that price is there on the blockchain for everybody to see forever. And then the smart contract uses it and determines whether or not to execute or to do something. So they arbitrate between parties in contracts using data. And so they act as a bridge between the blockchain and the real world. And they act almost like on-chain APIs to interface with off-chain APIs. They're queried by smart contracts for information. Could be any information, price information, weather reports, whatever. But oracles are also capable of sending information back out to the real world. So you can see kind of how video games become possible with scores and in-game items because of the oracles updating the video game software and then putting it on the blockchain and then letting everybody know. And then if there's a transaction, it can also send that, so on and so forth. So how does this tie into what we're doing? Well, we have the DPS, the data provisioning service. The DPS does not have to be DPS, and Dapper themselves have mentioned that. The purpose of the observer server, or one of the purposes of the observer server and access node, is to interface with these other services, which can be held on the local device, which can then feed information to observer servers or the access node. The first initial one is developed by Flow, which is the DPS. But somebody could come up with all kinds of different things which would act like oracles and which interface with the access node and with the observer service. So that's kind of how this ties in. So other questions? I see you're about to explode, Jim. You know you have
No.
about this.
Not explode.
It exploded excitement.
Oh, yeah, kind of. So Chainlink is an oracle. So does that mean Ethereum ties to Chainlink for the oracle, or are these oracles on Ethereum?
So the oracles actually live on Ethereum.
But Chainlink is an oracle in and of itself, correct? That's what it is as a blockchain platform.
We're going to talk a little bit about Chainlink later.
Okay.
We will get there.
I will hold my comments further.
Pradeep, questions about this? I imagine you have a whole bunch of questions about this because this is the development side or getting into the development side.
Oh.
I know we didn't really cover smart contracts, but I didn't want to go through all smart contract stuff and then get into this. I want to just get this out the way first before we get into like actual development. You can come back with questions later. You don't have to come up with questions on the spot. But if you do, let me know. So this ties into the DPS because basically anything Oracle can do, any service which interfaces with the observer service and with the access node should be able to do in the future, but locally. Okay. So we have a good 10 minutes. Let me see where we're going to get. So we still have we have a lot of, so this PowerPoint is really long, by the way. This PowerPoint is like 50 slides. So there's a lot of stuff on this PowerPoint. I went more in depth now that we understand it a little bit better. After the blockchain basics. Okay. Oop. All right. Mining. So we discussed mining very briefly. In the last PowerPoint. And we mentioned that mining is more relevant for Bitcoin than it is for what we're doing now. But we're still going to talk about it because there is still some relevancy for the test nets, and also because Ethereum used to run on mining, and also because it's good background information to know. And there is relevancy to this project in a tangential way. Mining is recording transactions. So what miners do is they're full nodes that collect transactions from various nodes, and then they put them into blocks. And then they try to add these new blocks onto the blockchain by guessing the mathematical puzzle, which is called the nonce. So that I think we know. Miners are rewarded by getting tokens. And in Ethereum, the mining reward is 5 Ether per block. And Bitcoin is 12.5. I think they just halved it last year to 6.25. So the way that miners work is there's something called the longest chain rule. So nodes always follow the database that has the most entries in it, the most up-to-date transactions. That's the longest chain. So blockchains with more blocks also consume more energy when you mine. So the mining difficulty becomes proportional to the blockchain size. And that metric is called chain work, which is a difficulty of work proportional to the length of chain, which means you need more processing power in order to deal with that particular blockchain and to mine on it and to get tokens. So chain work is almost like a business metric. The longest chain rule protects the blocks that are already mined onto the blockchain from being deleted, because whatever's already there will necessarily be included. And the longest chain rule resolves disagreements with two blocks are mined simultaneously. Whichever chain is longest will be went with first, and then the new block will be added to that chain. That way no transactions are lost. So that's how mining works. Why is mining relevant to what we're doing now? Because Ethereum has something called verification nodes. Collection nodes. So the collection nodes, they do the process, part of the process of mining by collecting all of the transactions, and then they get sent to verification nodes that put them into blocks. And then the verification, so miners are basically split up between collection and verification on Ethereum. And validation. Validation is after all the transactions are verified to be valid, then they're actually committed to the blockchain. So really 3 nodes with each purpose. But they're less computationally intensive because there's no nonce. There's no guessing the puzzle. So there's no need for a lot of computation. So it's pipelined up in a distributed system. So it's already distributed horizontally, like blockchains and all blockchains are, but it's that horizontal distribution is also pipelined up in the various node roles. So that's different than the way it works in both Bitcoin and Ethereum. So what kinds of mining are there? There's pool mining, solo mining, and cloud mining. Pool mining is when single miners can't effectively mine larger blockchains due to chain work. So they combine resources to mine the blockchain faster. Solo mining, every miner sets up their own hardware, registers it for mining. And then the first miner individual solves the nonce, informs everybody else. Then there's cloud mining. You just pay somebody else, which is all cloud is, to do it for you with their hardware resources. And you hire out other people's mining processes, and then you get mining rewards if it makes sense to even do that. So questions about this?
Yeah, no.
So this gives insight into, besides solving the mathematical puzzle, the consensus verification and validation nodes on Flow. Okay. So a little bit about miners themselves. Miners are just full nodes. They validate new transactions. They put them on the blockchain. They compute to solve mathematically difficult problems, which is just brute forcing cryptographic algorithm hash outputs to try and guess them. So they receive rewards when those are solved, and that can either be in the form of new transactions or gas fees. So how does mining work? You get the previous block header from the network. You assemble a set of transactions, which are broadcast on the network, into a proposed block. You compute the double hash of the previous block's header. You check if that hash is lower than the difficulty target. If it is lower, then you've guessed the nonce, and it's only going to be one set of numbers and letters is going to be lower, which is going to mean that the nonce is a guess. Proof of work is fulfilled. Consensus will be spread out by broadcasting it. You get the reward, and the block is committed. If it's not less, which most of the time is not going to be, it's only going to be less one time, then you repeat the process after you increment the nonce and try and guess it through brute force. Does that make sense?
Yeah.
So we have 5 minutes left. I would rather save Ethereum virtual machine for next time with this flow virtual machine. Hopefully Miklos, Sean, and Ruth can join us for tomorrow nights. So what I think is really instructive about this is that now that we understand the basics of the blockchain and we kind of have read the document, by looking at Ethereum, we can see why they developed flow the way that they did. We can see the reasons for everything that's going on, and we can also kind of see what do they expect out of things which should be coming in the future, not just in what we're doing now, which we've already have touched on, the access node, the observer service, and DPS tangentially by looking at the differences between Ethereum and what Ethereum did and what we should be doing, so on and so forth, but also for other things. So I feel like that insight, along with understanding Ethereum, is cool too, but that insight also has a direct material impact, I think, on what we're doing, theoretically or conceptually at least. So is there any just closing questions? Just leave it open for any kind of questions. Even on the old stuff, Pradeep, if you want to revisit anything old.
Yeah.
So can you even brute force crack a algorithm, cryptographic algorithm?
You can, depending on how difficult the algorithm is and how powerful your device is. So older encryption algorithms are simple enough that you can break them in a couple of minutes or even seconds with a regular computer. As time progressed, they made more and more complex ones, which are virtually impossible to break. Like SHA-256, you're not going to be breaking SHA-256 unless you have a quantum computer. And so that's what Bitcoin uses for its private addresses. So, for example, with like the Merkle trees, those encryptions, which I think Bitcoin uses SHA-256, is going to be too hard for anybody to try to brute force. Otherwise, it would compromise the entire network. But when you're dealing with the nonce, which is at the top of the block header, that is just difficult enough that it gives a period of time in which it takes somebody to brute force a break. And then as the blockchain becomes more mature, it becomes harder. As the chain work increases and there's more blocks on the network, it artificially increases that difficulty by making it harder and longer, and then you get more rewards. So originally breaking the nonce on a Bitcoin block was really easy. Anybody's computer can do it, take a couple of seconds. And you got a whole bunch of Bitcoin for doing it. But at that time, nobody knew about Bitcoin and cared about it, and it was worthless. As more people started using Bitcoin, cared about it, became more popular, then the Bitcoin network made the nonce way more difficult. It's to the point now that you need multiple servers to even have a chance at breaking a nonce.
Okay.
And so, and over time is going to get even harder to where only mainframes are going to be able to do it, so on and so forth.
Interesting. All right. Thank you.
No problem. So if that's our time. So if there's no other questions, I'm going to try to get through the entire PowerPoint in 3 sessions, hopefully. We'll see
Okay.
what happens. If not, then we'll just schedule some stuff for next week. I think we'll be able to get through it in 2 more sessions. So hopefully the dev team gets a chance to take a look at this, because I think they'll find a lot of it really interesting and informative. Okay, so if there's no other questions, I will talk to you guys
Appreciate it.
later tonight or tomorrow. No problem.
Okay.
Pradeep, I hope that was helpful.
Yeah.
I hope I gave you some insights. See you. Talk to you guys later.
All right.
Yeah.
Take care. Bye, Ali. Bye, Pradeep.
Sure.
Bye,
Sure.
everybody.
Bye.